Okay, so some of this will be review from in class, but this is our summary for 5.5 based on the activity that we did in class. Some of this should be familiar. We're going to look at expanding binomials, Pascal's triangle, and then finally the binomial theorem. So when we're expanding binomials, and this was part of your activity, that last question, a binomial is two terms. So when we are looking at binomials, it's anything with two terms, such as x plus y, x plus 3. We could even have x squared minus 4, 5x plus 2, anything with two terms. To expand it means to multiply into standard form. So if we raise something to the 0 power, and this is a reminder, if I have anything raised to the 0 power, it's just 1. So the expanded form here is just 1 when it's raised to the 0 power. To the first power is itself, so that's a plus b. To the second power, we have to distribute. So we have a plus b times a plus b, giving us a squared plus ab plus ab plus b squared, giving us a squared plus 2ab plus b squared. And then if I take that to the third power, a plus b to the third power means I have to take my a squared plus 2ab, plus b squared times a plus b. So distributing again, that's a cubed plus 2a squared b plus ab squared, and then times everything by b, so plus a squared b plus 2ab squared plus b cubed. And then collecting like terms, that gives us a cubed plus 2a squared b, not 2, collecting like terms, that's 3a squared b plus 3ab squared plus b cubed. Now the pattern that I want you to recognize is looking at just the coefficients. So for 1, that's just 1. Then 1a and 1b. Then we have 1a squared, 2ab, 1b squared. Then we have 1, 3, 3, 1. And what you should recognize is that this is Pascal's triangle. So the coefficients, as we expand our binomials, come directly from Pascal's triangle. And if we look at the expansion of Pascal's triangle and we keep adding rows to it, we'll start seeing bigger and bigger numbers. We talked in class about how our second diagonal here is the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8. Our next one would be 9. Our outside rows or diagonals are all 1s. And also that we have this symmetry, that diagonal one way is the same as the diagonal the other way. And then finally, in order to fill in the middle of each row, we can use the sum of the two numbers above it. So 8 plus 28 is 36. We can say 28 plus 56 is 84. 56 plus 70 is 126. And then 70 plus 56, we're going to have that symmetry all the way across the other side. Okay, so that's Pascal's triangle. Then the second number in each row is the row number. So this tells me 1, 9, 36, 84, 126, 126, 84, 36, 9, and 1 would be the exponents if I had a, or the coefficients, a plus b to the 9th. Then the last part we have to fill in is the variables. And in order to fill in the variables, we start with whatever our first term is, raised to the power, a to the 9th. And then we go down. So we have a to the 9th, a to the 8, a to the 7, a to the 7th, a to the 6th, a to the 5th, a to the 4th, a to the 3rd, a squared. I put that one really close, so let me write it a little bit farther away. A and no A. And then B goes the opposite direction. So B starting to the 9th at the end. B to the 9th, B to the 8th, B to the 7th, B to the 6th, B to the 5th, B to the 4th, to the 3rd, to the 2nd, to the 1st. Now, how do I know that all of my exponents are correct? Well, each exponent should add up to 9. That's a good double check. Each term, the exponents should add up to the same number that we raised to. This is called the binomial theorem. Okay, so let's see if we can apply it, and then I'll formally state the binomial theorem. The first thing we have to do is recognize what our a and b are. Now, it's not just one variable. In this case, our first term is 3x, and our second term is -2. Okay, so we have to look at the 5th row of our Pascal's triangle. I'm going to just make Pascal's triangle here. 1, 2, 3, 4, 5. And all I'm doing is adding up the two numbers above it. And so I know for the 5th row, my numbers are 1, 5, 10, 10, 5, 1. And now I'm going to fill in my a, which is 3x raised to the 5th, 3x to the 4th, 3x to the 3rd, 3x squared, 3x to the 1st. You can think of this as 3x to the 0, but that's just 1. And then b, starting from the bottom, b to the 5th, b to the 4th, b to the 3rd, b squared, b to the 1st. And then again, you can think of this as b to the 0, but that's just 1. So simplifying, now we have 1 times 3 to the 5th x to the 5th. This is 5 times 3 to the 4th x to the 4th times -2. 10 times 3 to the 3rd x to the 3rd times -2 squared. 10 times 3 squared x squared times -2 to the 3rd. 5 times 3x times -2 to the 4th. And 1 times -2 to the 5th. Simplifying further, 3 to the 5th, that's 81. Let's see, 3 times 3 times 3 times 3 times 3. So that's 9 times 9 times 3, which is 81 times 3, which is 243 x to the 5th. Now this is going to be 81 times 5. And remember, you have a calculator, you can use it. So we have 3 to the 4th, which is 81, times 5, which is 405, times -2, which is -810x to the 4th. Then we have 3 cubed, which is 27, times 10 is 270, times 2 squared is 4, gives us 1080x cubed. Now we have 3 squared, which is 9, times 10 is 90, times 8, which is 2 cubed. That gives us -720x squared. Then we have 5 times 3, which is 15. 15 times 2 to the 4th. 2 to the 4th is 16. So 15 times 16 is positive 240x, 5 times 3 times negative 2 to the fourth. That's 15. Negative 2 to the fourth is a positive 16, is 240. If you're wondering how I'm getting these numbers, I'm just multiplying. I'm following order of operations. And then lastly, negative 2 to the fifth is negative 32. Put it all together, and we get that 3x minus 2 to the fifth equals 243x to the fifth minus 810x to the fourth plus 1080x cubed minus 720x squared plus 240x minus 32. Okay, so binomial theorem is each part. We have the coefficients, we have our a's, and we have our b's. Put them all together, and we can get our polynomial without having to multiply 3x minus 2 times itself 5 times. If you wanted to check, you can try the long multiplication and verify that you get the same polynomial. Okay, so here's the formal statement of the binomial theorem. I put this at the end because it's confusing with all of the variables. So what does this mean? It means if I have a binomial raised to a power, we get its coefficients, all of these p-values, come from Pascal's triangle. Then we have a to the n, and we subtract 1 from the exponent for each term. And then going backwards, we have b to the n, subtracting 1 exponent for each term. That's all the binomial theorem says. So we have Pascal's triangle, P0, P1, P2, all the way down to P sub n for the nth row. And then we have a to the n minus 1, n minus, a to the n minus 2. And then this will be a to the 1, a to the 0, which is just 1, b to the n minus 1, all the way up, b squared, b to the first, b to the 0, which is just 1, and then we add them all up. That's what the binomial theorem states. That prevents us from having to multiply a plus b times a plus b times a plus b times all the way until we have n of them. That would be a lot of distributing, right? And then a lot of collecting like terms. Okay, so I'd like you to do these 4 problems as a lesson check, but we are also going to look at the next section because I wanted to introduce this next section so that we can look at it all together in class, next class. So in part 6, we're looking at graphing transformations. Now we've already done this for lines, we've done it for parabolas, we've mentioned it for any polynomial, we can do these same transformations. So we're gonna look at it with our higher degree polynomials. Now, what we have to remember from last semester is that when we have a function, if we multiply the whole function, that's a vertical stretch. So remember when we had something like 5 times x squared, we had x squared, and then we stretched it by 5. So it became a very skinny parabola. Okay, if we have 1/5 times x squared, then we have a parabola, and then the 1/5 makes it much wider. We squish it or compress it to 1/5 the height. Our minus h was a movement right. So this was stretch up and down. K is a movement up or down. So I should call this right or left. Right, so H and K are shifts. A is a stretch. So what I want to do is looking at the example here. What is an equation of the graph of x cubed? So we're going to start with x cubed. Vertical compression by 1/2. Vertical compression. So I want 1/2 times the height. So that's going to be the whole function times 1/2. Not within the cubed though. 1/2 times the whole thing. Okay, we want to reflect it across the x-axis. Well, if I reflect it across the x-axis, I'm making the y value negative. So that's going to be a negative in front of everything. And then a horizontal translation, 3 units to the right. So to move something 3 units to the right, h equals 3. So now we have 1/2 times x minus h, so that's minus 3 cubed. And then a vertical translation, 2 units up. 2 units up is k equals 2 plus 2. There's our function. So we took each of the transformations that we applied already. Remember, we did a whole project on that, on parabolas, right? So we're using those same transformations, but now for higher degree polynomials like x cubed. Okay, so let's do a critical thinking check. We have a, h, and k that are real numbers. We have here a cubic function, and we want to know how many zeros it has. Well, let's start out with the basic shape of a cubic function is like this, right? We know that x cubed has this shape. Now I'm going to multiply it by a and a negative. Remember what that negative did on our last problem? The negative flips it upside down. So now we have something like this, and it might be it's stretched somehow, but that doesn't really change its shape, right? So now we have negative a times x cubed minus h moves it sideways. Well, that's okay because I didn't draw a y-axis. So negative a times x minus h cubed, and then plus k. So that's going to move my x-axis up or down. So we have this, and it could cross here or here. Negative a times x minus h cubed plus k, right? If k is positive, our x-axis will be down here. If k is negative, our x-axis will be up here. Either way, no matter which of these graphs we look at, there is only one 0, one x-intercept, right? So the answer here is B. Okay, now the last thing I want to talk about is power functions versus polynomial functions. We've been using polynomials this whole time. So a power function is a times x to a power, right? Now, for a polynomial, we can only use only use whole number exponents, right? It had to be positive, it can't be fractions, it can't be decimals. So polynomials, 1, 2, 3, 4, 5, 6, 7, all acceptable exponents, including 0, right? X to the 0, absolutely fine, that's a polynomial function. For a power function now, a times x to the b, where a and b are non-zero real numbers. So b now, our exponent cannot be 0 for a power function, where it could for a polynomial function. And our exponents now can be any other real number. So they can be negative, they can be fractions. For a power function, our exponent can be any real number except for 0. For a polynomial function, it could only be our whole numbers, including 0. So what I want you to do, think about what I just mentioned. I gave you examples that will work to answer these questions. Give an example of a power function that is not a polynomial function. So which one works for power but not polynomial? And then give an example of a polynomial function that is not a power function. Okay, something that is a polynomial but is not a power function. And then I'd like you to complete these last 3 problems. So there are 7 problems that you're doing for homework, 4 from section 5 and 3 from section 6. And then we will dive deeper into this next class.